Now that you're aware of some important properties of exponential functions and natural logarithm, we'll try to explore two more memorable equations.
And as you remember from the second part of our video, we said that the integral of 1 over x is ln x, and we also derived that the derivative of an exponential function e to the x is the function e to the x itself.
And after we complete our journey, we'll head to ADA in order to derive these two equations involving e to the power of x and ln x that we'll be talking about in the third part of our video.
Logistic function is extremely useful in modeling the growth of population and giving some realistic approximations of populations in the nearest future, given that we know two reference points in the past. It's originally written in its differential form, which may be quite descriptive, but again, it's not that useful if we want to find the population at some particular point of time. So we'll have to use this equation, and to do so, we'll rely on our knowledge of differential equations, which are heavily based on integration techniques, which are basically just the ways to find and evaluate integrals.
Now we'll start with the differential form of logistic curve, and I'm gonna first write it down. It goes like dp over dt is k times p L minus p. And I'm gonna explain what everything means here. So first of all, let's start with this one, dp over dt. That's kind of slope. We've covered it in the previous hour series. That's just the rate of change of the population per unit of time. Don't worry about these, it's just a notation. It just means the rate of change. Rate of change of the population over per unit of time. K is just the constant of proportionality. It's just here to
just scales down the things. For example, like for the Earth, if we have billions of people,
yeah,
but they're not growing that fast, it just like we use this constant to correlate this, like the units.
Yeah, exactly. It's just the proper word. It just correlates properly the right side to the left side so that the numbers are correct. You don't worry about this one as well, because either it is given, or you can find, knowing 2-3 points or initial conditions, you can find the value of k. P is the population. P is the population. It's the number of things you have in the environment. So if you look at this part, only this part, and if we try to interpret it, it means that...
Yes, that's directly proportional.
Yeah, the rate of change of the population is proportional to the population.
It just basically means the more people, like the more individuals are there in a given population, the faster it grows.
Exactly. And I think that makes sense, right?
Yes.
If you have more people, the growth also increases, and the more people you have, the faster they grow. But in our real world, the growth doesn't only depend on the population. It also depends on the space left, right? So here we have to look at this part. So L is the capacity of the environment. It's just the maximum number of people that can live in that environment, in that ecosystem. So L minus P is the space left. So the growth depends directly proportional to the population and the space left. And I think that makes sense as well. So that's why this is the better approximation than just the exponential growth, because it also accounts the space left, the capacity.
But I have a question. Like, for example, we're generally using the divide dx notation, but here it's dp dt.
Yeah.
Like, so in this case, p is just like
y
value, like the function.
Exactly. If we compare Yeah. So the calculus students, calculus 1 students, they're used to this kind of notation, dy over, dy over, dx. So if we compare, t is x, so t is the independent variable, yes, and p is our dependent variable, is our y. So that's a good point because now if we want to predict the future, right? If we want to, for example, let me erase this part. So if we know the population in 2010 and we want to predict what will happen in 2050, so we know t, but in this form, we don't have t. So we only have population. So this form is not suitable to predict something. So we have to solve this, find the general solution, so that we can predict our population knowing any value of t, any time. So this is differential equation. The way we're gonna solve this is called the separation of variables. So it means that we collect the y's to one side and we collect the x's to the other side. So in our case, y is this one, and this one. So we have to collect them to, you choose the side. So in our case, I'm gonna collect all the y values to the left side. So
such that the differential should be in the denominator.
Yes. So I'm gonna p l minus p, and that equals to, I'm gonna leave k because k is a constant. K is just a number, and I'm gonna move dt over here because it's kind of x. So yeah, here we are. And now we can integrate both sides.
Well, with the right-hand side, it's quite simple.
Yeah.
We can integrate it
very
very
simple.
simply, but
just find it, but
It's just a number.
Side is more complicated, and I don't think that we have ordinary ways to solve it.
Yes, because we have two variables, and there is
yes.
a multiplication sign between them, and all of this stuff is in the denominator.
Yes.
There's not a simple way to solve this because the integrals, if you're familiar with the integrals,
Yes.
you know that integrals are crazy things, so it's not easy.
we do not have a quotient rule, so we cannot just
Yeah.
find it.
So we have to apply a special technique to solve this part. And that technique is called, I think
I'm familiar with this kind of techniques. Is it partial fractions?
yes, partial fractions. I don't want to show this.
But I
Maybe
know
you
how to
know.
solve it. Can I show it?
Oh yeah, exactly. So this is yeah.
As Mr. Elnur has shown that this form of integration is very complicated, and the technique that we mentioned is called partial fractions. So in order to solve it, it's the best way to opt for if you have some complicated structure with several variables in denominator, and you can just simplify this whole fraction into two or even more simple functions and fractions which will be easy to integrate. So I can show you an example in order to get familiar how we use partial fractions. So let's take 1 over x squared minus x minus 2. So you can see that it's a simple way for you for the first glance, but if you look more deeply, you see that x squared and minus x and also in the denominator is not such a simple thing to do. So we do the following steps. We can separate it into two additions of fractions. I can write the form in order for you to be more close to the equation yourself. So if I see here the roots, I know that the roots are 2 and -1. So I write here in the denominator, I separate them as x plus 1 and x minus 2. So here's minus 1 and here's 2. So I don't know what to write in the numerators, and that's why I write here just a and here just b. So so we write this way because if we if we're given this part, and if we do common denominator, we'll get the same thing in the denominator.
The common denominator will be the multiplication of this one times this one, and that will give you That's,
so you're just factoring the polynomial in the denominator.
Yes, I just do factorization, and in order to get the common denominator, I just multiply x minus 2 to a and x plus 1 to b. So I write it in that way. minus 2 plus b x plus 1 divided by x plus 1 x minus 2 and is equal to this function. So these denominators are exactly the same thing, and I have only to work with numerators. That's why I just copied this equation from here. So in order to find a and b, I just substitute x as 2 here and x as -1 here. So if I substitute 2 instead of x, I see that it will be equal to 0 and our a will be cancelled out. And if I substitute 2 here, we'll get that b multiplied by 2 plus 1, which is 3, is equal to 1. So I can get that b is equal to 1 over 3.
So we can substitute anything we want
Anything
here?
we want, yes. It's not.
Okay.
It's much easier to solve for 2 and -1 because you will get zeros.
Yeah.
But you can just plug in 3, 4, 5.
And
Yeah.
if you plug
whichever you
if
want.
you plug different numbers, we'll just have a system of
A
equations.
system
Yes.
of equations, and they will have
Easier to
solve,
plug
yes.
2 and -1.
negative
Yeah.
1, yes. So, and I substituted 2, and now I want to substitute -1. So it will be equal here to 0, and b will be cancelled out in such case, and it will be equal to a multiplied by -3 is equal to 1, and a is equal to -1 over 3. So I have found what a is equal to and what b is equal to. And if I substitute my variables here, I can write it in a better way, like 1 divided by 3 x plus 1 plus -1. I can just remove a plus from here, right? The minus sign, 1 over 3 x minus 2 is equal to 1. Here is how to use this technique in order to get the easy fraction. And if you have to integrate this one,
Sorry, I think
not to 1,
okay.
to this kind of thing, to 1 over x squared minus x and minus 2. So you can't integrate this one, but you can integrate them separately.
I think that's reversed, right? Just in case a is negative. So negative here, -1/3.
Oh,
Right?
oh,
Yeah.
right, yes. A
And
is
the
negative
plus,
and
yeah.
it's plus, yes.
Perfect.
Yes.
So now,
Can
for
we
now,
use like this technique to separate the fraction we
Yes,
had
yes.
originally?
yeah,
This
I think
is
yes.
the-
Now you may not be like familiar with this, or you may not understand why this is, but it's easier to find integral of this separately. I'm gonna
Yes.
explain later. So yeah, that's great.
Thank you.
Now we'll apply. I think now we'll apply to this,
Yes.
right? Yeah. Okay. Great.
Thank you. So if I write here the equation that Mr.Elnur has written here, we can see it here. We don't take dp because it's inside the integral, and we just take 1 over p multiplied by L minus p.
And in this case, p is our variable,
P is our variable.
and L is just a constant.
Yes. And you may somehow presume what I'm going to do next, and if you know, please leave your suspicion in the comments, and we'll be interested in your solutions. So now I would like to do the same thing in denominators. I also write the fractions with addition, and in denominator you see that there's a multiplication sign there. That's why I write p from this denominator and L minus p for this denominator. I write just a here for numerator and b here for this numerator in order not to get somehow scared by these too many variables. So if I write a multiplied by L minus p plus b multiplied by p, I do the same thing, and I get just a common denominator, and I multiply divided by p multiplied by L minus p is equal to 1 p multiplied by L minus p. So these denominators are exactly the same thing, and we get just the same kind of equations that in my previous sample. So I just copied this one, a multiplied by L minus p plus bp is equal to 1. So here I can substitute 0 for L and 0 for p. If I substitute p here instead of L, I get that p minus p is 0, and my a will be cancelled out, and I just get that bp.
You mean BL? Like
I
you substitute L
substituted
instead of P?
BL is equal to 1, and b is equal to L in such case. And if I substitute
To the -1,
yeah,
like the power of -1.
b is 1 divided by L. So if I substitute L for A, I will get the same thing with A. L is equal to 1. So I'll get that A is equal to 1 over L also.
Great.
So if I write it here for A and for B, I'll get 1 divided by LP plus 1 divided by, I substitute L also here, and I'll get L minus P, which is equal to L squared minus LP, which is equal to 1 over P L minus
Original fraction.
original fraction. So you can see that this way is much easier for us to comprehend than that one, and you can find these integrals much quicker than you have to suffer with this equation.
Yeah, and for you, you can pause the video, solve this one, like do the common denominator, see whether this part is equal to this part. Just a challenge for you if you're really interested in this one. So maybe we're lying, maybe we're inventing stuff. So
Which is unlikely.
yes, because it's a math. Maybe just solve the common denominator. See if you'll get from this to this, right? Just pause the video. And now I'm going to continue. I'm going to find the integral. So I know that this part is this part. So I'm going to copy that. So that's an integral 1 over. Let me take 1 over L out of the brackets. So I'm gonna then take 1 over L out of the integral even. So here 1 over L. I think it's visible. So here I'll get 1 over P plus 1 over L minus P dP. A very important thing in the integrals. And here I have K dt. Great. Now this one is easy. This one is easy.
Yes.
This one kind of easy. We have to be careful about something, but it's also easy. So again, I don't change this one because it's a constant. It's just a number.
Yeah.
1 over P, the integral of 1 over P, anyone.
Like we had integral of 1 over x, but in this case, it doesn't really matter what our variable is because integral of dx over x or integral of dp over p, the same thing. So we'll have a natural log there.
Yes, exactly. So we have ln
of
p, natural logarithm of p, plus maybe some of you who are watching over there think about the integral of this one. What is the, and remember, this is just a number. This is just a 2, 3, I don't know, any number. It doesn't matter. Something minus p. What is the integral of this? Think about it a few seconds. I'm going to write it down. So that will be also natural logarithm because anything in the denominator that will give me natural logarithm. But here's the one tiny thing is that there is a negative sign in front of the variable. So I have to, when I find the integral, I have to divide by this sign or by this coefficient. So I divide by -1. But I'm not gonna write it as this. I just will change the...
And it just happens because if we find the derivative of ln L minus P, then we'll have an, like the negative sign in front due to the chain rule.
Because of the chain rule, yeah. Yeah, that's the integral of this part. I don't have to write dp no more, anymore, because I found the integral, and the integral of the right side, again, this is just a number, this is just a 2. Think about, again, just pause the video. You can search the Google, what is the integral, say, of 3, for example, 3 dx, whatever, 3 dt or something. What is the integral of this? And if you know, the derivative, you can think of whose derivative is 3, because because the integral is just the reverse of derivative. Whose derivative will give you 3? Think about it.
And the answer was?
The answer was
3t.
3t, yes, 3t, 3x, yeah, that's kind of. Now we don't have 3, we have k, so we'll have kt
plus c. So do not forget to write this letter. It's very important. You can see that c is just a letter, but it carries a deep meaning.
Yeah, and actually I have a question. Like, why don't we have like plus c on this side as well?
we have,
but we don't.
But we don't have.
Yeah, because I just moved this C to this part. It's kind of
to be or not to be, like.
We subtract one C from another C and add the third C.
You write the C plus C to both sides at the start.
Yes.
But I moved this C to this C to this part.
It's not this C that was in the first part.
Yes,
it's
this C is different C. Whatever, just write C.
Okay.
C is just a number because and one more thing, it's just not the letter. To your surprise, it's a number. So now we can use the properties of logarithm.
We actually use them in the second part.
Yes. And we can combine them.
Yes.
So we'll have ln.
Yes.
You get write subtraction like a division.
L minus P.
When you have minus sign between logarithms, you just divide the things that are inside of these logarithms. And I want to move this L to this part, to this side. I don't want to write 1 over L every time here, so that will be more aesthetic.
L
yes.
Plus LC, but you'll definitely write just C.
Yes. Plus C.
What crazy things are going there? Like CL is the same as okay.
Yes.
Yeah.
Because it's just a constant. I multiplied constant by another number.
Yes.
I got another number, and this number is C, but this C is different from this C.
And also all the previous C's.
Yes, all these C's are different C's. This C is different C. Okay. Now the last part is to get rid of this ln. So how we can get rid of this ln?
Exponentiate both
sides.
Yes.
So we have. I don't know if it's visible from this camera. Is it right? Yep. So we'll have e to the power of KLT plus C. All right. So this the issue is that I can separate when I have plus sign in the power.
Yes.
I can separate. I can write e to the power of KLT
multiplied by
multiplied
to the power of C.
By e to the power of C.
Equal to C.
So let me write it. I'm gonna erase now, but for you, I'm gonna write it here. It's K times e to the power of KLT
plus C.
I'm gonna write multiplied by
e to the power of C. Oh, all right.
Okay.
Think about by yourself. Is this one is the same as this one?
Yeah.
You have the rule that when you multiply, you add the powers. When you add the powers, you'll get this one, right? So this is the same thing. And e to the power of C, e to the power of C is just a number.
Yes. And you see.
So it's C.
It's a third C. Like
yes. And disclaimer: this C is different from this C, which was different from this C, which are very different.
Which was different from the C that you didn't write on this side.
Yes, yes. So I'm gonna just copy that here, e to the power of KLT times C.
Okay.
I know that's long, so really the solution of differential, like the logistic curve, is very long. So we wrote it down here. Then we what we do? Separation of variables. Then we learned. Yes, Nurlana showed us that we can we can use partial fractions
to decompose
into two fractions. Then we integrated both sides. Then we used every step is just a different rule from the mathematics. Then we apply the rule of logarithm and then the exponentiation.
Yes.
The last part.
We'll have to solve for P.
Yes, we have to solve for P. Now remember why we do this, because we want to find the formula.
It gives us population with respect to time.
Yes, at any time.
Okay.
If we have like 2050, we can substitute some value here and we can predict the population in 2050. So that's the ugly form. We can work with that as well, but that's not that's the ugly. We want to solve for P. So we want to have one P here and everything on the right side. So the final phase. P over L minus P. I just copied that. I don't know why I did that. Anyway, so what I do, first, I just flip the fractions. All right, I just flip this part and flip this part. You'll understand why I do this. So I'm gonna have L minus P over P, and I don't want to flip this. I just will write e to the power of minus KLT, right? That's the same as flip. That's because if you have a negative sign in the power, it means that you flip. And times, you flip this, and I'm gonna write it C, which is again yes, this C is just a 1 over C. This again one more C, which was different from the other C's. So here we can divide separately L over P minus P over P. When you have one thing on the denominator, you can do this. You cannot do this when you have minus sign on the denominator. That's why we flipped it. Now we can just divide L over P minus P over P. P over P, which is, as you can understand, is just a 1. I just move 1 to this part. Oops, times C plus 1. And yes, I think we solve for P. We can flip one more time. We can use cross multiplication. There is a triangle rule in physics you can apply to find the P. There are like a bunch of different rules. So I'm gonna write it down. L over e to the power of blah 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 blah
C
blah blah.
Okay.
That's L. That's the end, by the way. You can relax. That's the end. Now that we solved for P, now if we have some, for example, we know the population in 1990, for example, and we know the population in 2010. We can substitute this here, and we can find the value of K and the value of C. L is just the capacity. We know the capacity, or we can just find the capacity. And that way we can predict what is the population in 2050, 2010, or 2000 in the future. So this formula will give you the population at any time in the future. That's it.
Yeah, and it's certainly not the thing that our original function could do, because we didn't have time as a variable there.
Yeah, the original function gives just the rate of growth of the population, the rate of change of population at any given time, but it doesn't give the
population as a function of time.
Yes, it doesn't predict the population itself. Yes. So that's the different thing. So that's why we needed this, because it's more useful data when we want to work with the populations.
So now that we have solved for P in our differential form of logistic curve, we would like to plug some values to model the growth of population on Earth. So I will start with a year 1980. So at time 1980, so it will be our reference point. The population of Earth, as I've researched, was around 4.5 billion people. And 20 years after that, in year 2000, population was around 6 billion people.
Those are official data?
Yeah. Actually, those values vary from different sources, but it doesn't really matter for our purpose. And also, I've read in one research paper that the maximum capacity of our Earth is 10.5 billion people. And again, these estimations also may be different in different sources, but it's some approximate number that will be sufficient for our derivation. And also remember from your derivation that the equation had this form: P as a function of t is L divided by 1 plus C raised to the power of e negative k times L times t. So now, because it will not be quite convenient to work with these years, to plug in here something like 1980, I will write it differently. I will take this as year t0, and then, because the difference is 20 years, this will be the year 20. So the first thing to do, if I plug 0 in this function, this whole term will become 1 because e to the power of 0 is 1. And I know that the population was 4.5 billion people with a maximum capacity of 10.5 billion. Then I have this term here, c, and the whole this term, as I've said before, becomes 1, so it will be just c. And now I'll have to use my calculator, or actually I could actually calculate it myself. 4.5 times 4.5 c is equal to 10.5, so 4.5 c is equal to 6, so c will be equal to 1.3333, something like that. So I found the first constant, and there's also some second constant, k, that we'll also have to find to write the function. And to do that, I will use a second point. So the population of 6.0 billion people, fraction, the limit of population, like the capacity, is 10.5 billion, 1 plus, now I have this value for c, it's 1.333, e raised to the power of negative k, which I don't yet know, multiplied by L, 10.5 billion people, and by time. My time in this case will be 20 years. And actually it will be impossible to solve it manually, so please give me my calculator. Thank you. So I will just solve it. 6.0 is equal to 10.5 divided by 1 plus 1.333 e raised to the power of negative k times 10.5 times 20, and I want to solve for x, so find x. And the answer I have here, k, is equal to 2.7386, something like that, times 10 to the negative 3. So it's the second constant. And now I will plug those constants in the original equation to write the function. But actually, let me change the color. For example, yeah, green would be fine. So the p of t is equal to, a bigger fraction here, 10.5, 1 plus 1.333 e raised to the power. So actually here I will have two constants, 10.5 and this one. So we could actually combine them to one new constant, and again we could use a calculator for that. So we'll multiply this answer by 10.5, and we'll have a new constant which will be 0.02876 and our variable time.
Great.
So we have the function that will model population of the Earth at any point, like at any instant of time.
Great.
And the main point here is to sketch it. So at time 0, and I have already like x, y axis, and my reference time is 0. It's a time that elapsed since 1980. So at time 0, my population was 4.5 billion people, and 20 years after that, here, my population was 6 billion people. So let me find that point. So it's here. And I will use this information. And also there's an important fact about logistic equation, that the population grows at the maximum rate when the population is just half of capacity. And half of my capacity will be around 5.25 billion people, so around somewhere here. To some point, I am not sure whether it's at 10 or somewhere in this interval. And the main thing that as our time approaches infinity, the population will approach our carrying capacity. So there will be some upper limit here. Here, like 10.5 billion. And finally, we could actually draw it. So, yeah, something like that. So it will be. So it's growing like that. And here, well, it's not quite. And as population grows, it will slow down like that. Yeah, it's not the best curve.
I think we can move this to here, something like that.
Let's put it here.
Yeah, I think that way it will grow faster at this point, something like this. So it grows fast. Oh, okay, something like that.
And then it slows down.
And then it slows down. But it slows down approaching this
this infinity
value, right? Okay. Okay, something
like that. And actually, the main thing, we could use this equation to find the population of Earth in 2020, or let's actually use 2022, like this year, or 2021, like the last year.
Okay.
So we'll have to plug here. We'll have to plug 41, like 41 years after 1980. So it will be 10.5 divided by 1 plus 1.333 e raised to the power of negative 0.02876 times 41 years. Okay. And by our estimations, the population at 41, so it's 2021, should have been 7.447 billion people. Yeah, actually knowing that the actual population that year was around 7.9 billion people, we could find the error of our estimation. Like we could subtract this value from the actual value, like 7.9, the actual value minus the value that we just found. And we'll divide it by actual value, 7.9, and multiply it by 100 to find the percentage error. And what I see here is that my error of approximation is 5.7%. So it's really close to the real value of population. And yeah, that's it. That's a logistic curve. And also you may have heard about the exponential growth.
Yes, and perhaps everyone will want to ask us the question, why can't we use exponential function in this case? Why we always refer to logistic
That's
function?
a good question, and you guys may actually ask it.
Yeah, so let's make comparisons.
Yeah, we could compare the exponential curve and the logistic curve and explain which one is a better approximation.
Approximate, yes.
So now we will compare the logistic model of population growth and exponential model.
Yes. And in the following graph, we can see that the blue one explains our exponential function, while the black one explains our logistic function.
And in our plane, the x stands for time.
Yes, and while y stands for population.
Yeah, and just specifically the x, like we plotted x in years.
And plotted y in millions.
So the both functions have the initial condition, like when time equals 0, our initial condition is 5 million people.
Yes. And we can see the growth which begins between the duration of 0 and 14 years. At first they are quite close to each other and they just have not so significant discrepancies between them. And we can see that logistic function even has a little bit overestimation because the value of exponential function is always lower in this duration of time. And at 14 years, they just intersect at one point.
They're just the same,
they are the same, which is quite below, just below the 10 million people.
And just to remind you, like we have the upper limit of 10 million because like here in our function, the carrying capacity of your population is just 10 million people. So like as time approaches like some big value, your population will come closer to 10 million people.
And after 14 years, we can see that exponential function has no bounds and just continues to rise. Even not so slowly as the logistic function does, while the logistic function just flattens out, but it never reaches the value of 10 million people.
And after some particular, after this particular time, your exponential function is just a great overestimate of what's happening. And so just for that reason, like this function is more realistic.
Yes. Well, we know that exponential and logistic function can be used to model the population growth, but we know that exponential function here has overestimations, and I think that logistic function has quite interesting applications, right?
Yeah, for example, in like you can think of some applications in biology, because like in real life, in nature, there's certainly no such thing as an unlimited resources, because like your sources, your areas are always limited, and as your population density
just overpasses some limit, the population will grow slower and slower, and so just for that reason, it's a good approximation of what's happening in nature. And as your sources become depleted, your population will not be able to grow any further, like over any limit.
Yes, and while considering the population growth, we should bear in mind that the resources are not always plentiful and available, and there are some limitations on the growth.
Yeah,
that's
so
why logistic function, I think, is the
it's a better
best option.
it's a better model to explain, to describe the growth.
Still, the logistic function is not the most precise one.
Yeah, because it only considers the space available, but still it's better than exponential.
It's much smaller than that with the exponential function.
So that's difference between them. Yeah, that's it.
Now that you know so much about logistic curve, let's focus on one more amazing function that is called the gamma function.
Well, gamma function was created by Euler and its alternative definition for the factorial. Just to remind you, the factorial is a multiplication, just a product of all the numbers between 1 and the following natural numbers that you're trying to find. You just take all the previous subsequent numbers and multiply them. For example, 3 factorial is 3 multiplied by 2 and multiplied by 1, while 5 factorial is 5 multiplied by 4, 3, 2 and lately 1. And I'm quite curious about finding different factorials of integer and non-integer numbers, and 0 is one of these mysterious values that I would like to find the factorial. And I think that the gamma function will be the exact and precise techniques that we'll apply to, and let's try to find it.
So now we'll try to prove the gamma function. The first thing I'll do, I'll write the expression for gamma function. So it's written as n factorial is equal to integral from 0 to infinity x to the power of n multiplied by e to the power of negative x times dx. And I put the x here because I'm differentiating this function with respect to x. So what I'll do now, I'll start with a different integral expression and use it to derive something that's similar to this one, and then use it to confirm this expression. So the integral I'll start with will be from 0 to infinity. So the thing I'll do now, I will leave this polynomial term and use it, write only the exponential term here. So it will be e to the power of negative. I will write not x, but x and some coefficient of a in front of it, like negative ax and dx. So from the second part of our video, you remember that the derivative of e to the x is the function itself, so its integral will also be the function itself. So the first thing I'll do, I'll write the function itself, e to the power of negative ax. But if you are integrating, you'll have to divide by the coefficient in front of the variable, and my variable in this case is x. So the coefficient in front of the variable is negative a, so I will divide it by negative a, so I'll write negative 1 over a. And the next step is integration, is of course putting the bounds. The lower bound is 0, the upper bound is infinity. So first we have to put the upper bound. If I plug infinity instead of x, it will be just negative 1 over a e to the power of negative infinity.
That is 1 over e to the power infinity?
Yeah, it's 1 over e to the power infinity, and actually these coefficients do not matter because we're dealing with infinities here. And if I'm dividing 1 by some infinitely large number, it will approach 0. So we can write just 0 here. Then I subtract this function, the antiderivative, and I plug 0 here. And if I plug 0, because anything to the power of 0 is just 1. And this term will become 1, and I'll have negative 1 over a. Negative 1 over a, and it just becomes 1 over a. So I'll now rewrite both sides here. Integral from 0 to infinity, e to the power of negative ax dx is equal to 1 over a. So the thing I'll do now, because these two expressions are equivalent, I can differentiate both sides. But here I only have one letter, and I will assume that it varies, so it will be my variable, and therefore I will be taking the derivative with respect to this letter, like to this variable a. So here I'll write d over dA, and it's Leibniz notation for the derivative. Here I'll write the same thing, d over dA, and parentheses here. So in the right hand side, as you remember, Nurlana told about power rule in the second part.
Okay,
well, yeah,
yeah,
and actually we can rewrite it
as a to the power of negative
1. As a to the power of -1. Then we'll use this rule. We'll bring -1 as a coefficient and decrease the power by 1, so it will become
2.
Yeah, its new power will be -2, and it will be -1 over
a squared.
Yeah, a squared. So it was quite simple on the right hand side, but the left hand side is more interesting because I'll have to apply the technique that's called differentiation under the integral sign. So this technique is used when I'm trying to differentiate an integral. So first of all, I am allowed to move this like derivative sign inside the integral. But I'll have to use a different notation because here I already have a differential, and to show that I'm trying to differentiate this function with respect to a, I will use this notation. This is called the partial derivative. And what a partial derivative means, it just means that for this function I will view a as my variable and everything else is just some constant values. For example, x will be just some constant. And if I'm trying to find the derivative of again, it will be the function itself. So let me write it. Here. So integral. So it will be the function itself. And by the chain rule, I have to multiply by the coefficient that stands in front of the variable. But in this case, as I said before, the variable is a. So the coefficient in front of the variable, it's -x. And the right hand side is the same, it's -1 over a squared. So this expression is the first derivative of this integral with respect to a. So now to see some pattern, I'll have to differentiate it several more times. So let me find the second derivative. Again, on the right hand side, it's the same logic applies. Yeah, it's power rule. So what we're doing here
as a to the power of -2, then decrease the power by 1, we'll get -3, and we'll multiply by -1, and you'll get just 1 over a squared.
Okay, it will be negative. Negative will disappear because we'll multiply by -2.
In front of it.
So it will be 2
divided by
a cubed. Yeah, right. And here, if I differentiate the function one more time, again, this will be the same function here, but I'll multiply it by a coefficient in front of the variable, which is a.
It's -x.
Yeah, -x again. So
-x multiplied by -x will give you -x squared.
Yeah, -x squared. The same function stays here, and differential is equal to 2 over a cubed. So I guess we could differentiate it one more time to see the logic. So let me continue here. So I have this expression. -x squared power multiplied by e to the power of ax. Let me write it in here. Dx. And we have 2 over a cubed. So while I'm doing the left-hand side, you may try this one on your own. So I'll do this part at this point. So I'll differentiate it again. So did I figure out what this part is? Again, if you use the power rule, it will be 2 multiplied by a to the power of -3. Yeah, you bring -3 as a coefficient, multiply by 2. Yeah, it's -6. And if you decrease the power by 1, it will be -4. So here it will be negative 6 over a to the power of 4. Here again, you bring negative x as a coefficient one more time. So you'll get negative x squared multiplied by negative x. So it will be negative x cubed. The same function, the x integral sign on the left. And negative 6 to the power of, so divided by a to the power of 4. So now that we have found three derivatives of this expression, we may see some pattern. First of all, let's say if I'm trying to find nth order derivative, so it may be 10th derivative, maybe 20th derivative, whatever, dAn integral and the same function I started with. So what I see here, let's see, when I found its first derivative, I had negative x here. Then when I found its second derivative, it was negative x squared. Third derivative, negative x cubed. So I can now say that if I find an nth derivative, there will be negative x to the power of n. So yeah, let's write it. Negative x to the power of n. Negative a to the power of a x, the x and integral here. Then for the right hand side, I'll also have to see some logic. First of all, what you notice is that the signs are alternating.
Yes.
For example, here it had negative, then positive, then negative again.
So the
and
first will be positive again.
yeah, the first derivative will also be positive. So if I have alternating signs, so let me actually rewrite this integral. So if you have the alternating signs, guess what term we'll have to use? And did you guess it? It will be negative
1?
Yeah, negative 1 to the power.
Power.
Yeah, but we'll have to see what the power is. It can be n or n plus 1. So when n was 1 and n is equal to n, it means, yeah, it's first derivative. So
It's negative.
It's it's negative.
Yes.
Then for the second derivative, it's positive. For the third one, it's again negative. So I see that for every even derivative, it has to be like the positive, as you see here. So which means that if you plug, for example, 2, 4, or something, it will have to be just 1. So, and here I make a conclusion that it has to be n, because if I put n plus 1, it will be different. Like it will be positive first, negative then, and so on. Yeah. Then here on the bottom, you always see a to some power. So let's write it. And now let's try to see what's the power of a. So okay, let's see. This was the first derivative, right? It's 2. Then for the second derivative, it's 3, 4. The third derivative, it's 4.
So you just add 1 all the time to the n.
Yeah, okay. So we can write it as
n plus 1.
n plus 1, okay, which kind of makes sense. Let me check. When it was 3, if I plug 3 plus 1, yeah, it's 4, so the logic works. And the final thing is something as a denominator, because you see these coefficients. For example, for the first derivative, it was 1, then it was 2, then it was 6.
Which sector was 3 multiplied by 2 and multiplied by 1.
Yeah, and Nurlana has explained the concept of factorial earlier, and she said that factorial is so it's a multiplication of all numbers that stand before, like between 1 and some number n. So 6 is 3 factorial, and actually it's the third derivative. So we see,
n factorial.
yeah, it's just n factorial. For any nth derivative, it will be n factorial. And if you pay attention to this expression, like the original integral expression we had here, you see that we're pretty close, but we'll have to do some modifications.
With a.
Yeah, with a and with this negative sign, because I do not have a negative sign there. So what I'll do, let's write it in this way. So I can expand this term by writing that it's negative 1 raised to the power of n multiplied by x to the power of n multiplied by e to the power of negative a x dx. And nothing will change on the right hand side, and factorial
Now we can eliminate -1 to the power of n's.
Yeah, exactly.
First we have to move out that.
Yeah,
can we move out that?
And we can do that because this term does not depend on x, like on the variable with respect to which we are integrating the function. So if you write -1 to the power of n here, it will be just cancelled with this one. And what I have here, so it will be integral. So now I can just, let's make it this way, so I don't have that term anymore. And the last step here, there's nothing in front of x. Actually, there's just -1 in front of x. So just to make this happen, I'll have to put 1 instead of a. And
a was any number.
yeah, a was just some variable number. And so it will be x to the power of n, e to the power of negative. I will now write x. This a and this a are just the same. So if I plug 1 here, I'll have to plug 1 here.
N power is just 1. So.
Yeah, it's 1 and 1 raised to, like the any power, it will be just 1. So I only have n factorial here. And what you see here is that we have just demonstrated that we can like expand the factorial and write it as an integral. And actually, I see that there are many opportunities that this integral expression offers to us. For example, we may plug like whatever we want, even.
Can we like put irrational, like integers? It's okay.
Yeah,
like, can we find the irrational integrals or zero integral? Let's start with the zero integral.
Yeah, I guess it's possible because yeah. Actually, I'm quite curious about what the zero factorial could be. So yeah, let's try. Yeah.
Well, as Mr. Elnur has asked us how to find zero factorial, we will now use the gamma function in order to prove that it's equal to any value or even find if it's equal to anything. So I don't want to use a calculator at first and we'll do it manually. So as Ali has explained us, the gamma function is just n factorial, which is equal to the integral from 0 to infinity. Its bounds are 0 and infinity, x to the power of n multiplied by e to the power of -x dx, right? Yes.
Okay.
So if I would like to find zero factorial, I just substitute.
Yeah, we would plug 0 instead of n.
Okay. So 0 factorial is equal to the integral from 0 to infinity, x to the power of 0 multiplied by e to the power of -x dx. So what can I say here? That
first of all, we see x to the power of 0 is just
1.
Just 1.
Any value, not just x.
Yeah, it makes sense. So you can just ignore this term. But I have a question. How can you actually plug infinity as your upper bound?
This question is quite familiar for me, and I'll definitely use it.
Yeah, because I answered it.
We used it in the previous video. It's called improper integration.
Yeah.
And 0 factorial in such case is equal to, so it's just 1, I can just eliminate it. And
so you may,
yes,
okay.
thank you. And it's equal to, what happens here? Limit appears, limit.
Yeah,
let's take it
typical of improper
A,
integration.
And it approaches to infinity. Integral. Well, I write 0 here, but I
will
can
replace infinity with a.
Okay. With a, and it's e to the power of -x dx.
Okay.
So first of all, I would like to evaluate e to the power of -x on the integral, and e to the power to the n power is just the same function
itself.
And but use chain rule. You have to divide by this coefficient, and we can see -1 behind x, and we just will divide it by -1. So it's equal to -e in the power of -x. But
okay, just to make a remark, because if we find the derivative of this function, we'll have the same expression. But in this case, we are not. Like it's important to understand that we're not we're not multiplying, but we're dividing by -1. Like, but
it's
actually,
it's the same thing.
Yeah. If it were 2, it would be different.
It would yes, different. And I write limit as a approaches infinity. So I can substitute here a and 0.
Yep.
So let's the first evaluations. -e to the power of -a limit a approaches infinity.
And then you subtract
e to the power of -0, just 0. But we have minus in front of e as well. So minus e to the power of infinity is...
So you can write it as -1 over e to the power of a. It will be equivalent.
Equivalent to 1 divided by infinity.
And if you divide y by infinity, it will
0.
approach 0. Okay, so you can just write 0.
I can write 0, just keep this sign here, and minus and e to the power of 0, I can write just plus 0. Do not write any positive or negative sign behind 0.
Just
so
1.
It's equal to just 1.
And we have a negative sign in front.
And it will be in the brackets. 0 minus 1 will give us 1. So I have put that 0 factorial is equal to 1. And it's quite amazing because we know that factorial...
Yeah, factorials is just multiplication of all numbers between 1 and this number. And if you find...
0 and 1...
There are no integer numbers actually, but we still can find its factorial.
Yes, and let's prove it with a calculator. Let's see what it gives us.
Okay.
So, if I write 0 and factorial, 0, it's equal to 1. Yes.
Okay, so we were right.
Yes, we are right. Did everything properly.
But I have a question. What if we try to find, what if our n input is, let's say it's non-integer, it's even better, it's irrational.
Let's take pi.
Yeah, okay, the pi, one of the most popular rational numbers.
Pi factorial is equal to integral from 0 to infinity. Well, as n factorial is here pi factorial, we have to plug pi instead of n here. And
so it's x to the power of pi.
Multiplied by e to the power of -x, it doesn't change here, dx.
So now, this integral does not seem possible to be evaluated even with integration by parts. It would not give anything.
Yes, that's why I would like to refer to our calculator in this case. So let's write that.
Let's try pi factorial first.
At first, okay, let's write pi factorial.
It just expands pi.
The value of pi, it's 14, etc., and just sign of factorial.
Because I guess it does so because factorials only exist for integer numbers.
Integer numbers, and pi is not an integer one. That's why I want to evaluate this integer function.
Okay.
So I write the integer from 0 to infinity. Okay, x to the power of pi multiplied by e to the power of -x
and dx are differentiating. Okay. And here we have the answer.
It gives us the answer. 7 point. Let's write the answer here. It's approximate value
7.18808 705.
Well, it makes sense because
pi is just a little bit bigger than 3, and 3 factorial is 6. So this is just a little bit bigger than 6.
Yes.
Okay. And we have just calculated the factorial of irrational number.
Which the calculator is not able to do, and it doesn't have enough resources.
Yeah. So it's actually amazing what the gamma function can do. Yeah.